Hello everyone, welcome back to this online class. My name is Francis Okech and my YouTube channel is Professor Francis Okech. Today we are going to look at Calculus 1 and our main topic is on application of differentiation in univariate optimization problems. Now we need to understand what we mean by optimization. So I'm going to write. Now, when you talk of optimization, it simply means finding the maximum so this means finding the maximum or minimum values of a function, which may be subject to some constraints or not, which may be subject to some constraints or not. So then what is univariate optimization? So therefore, univariate here means that our function depends on a single variable. So in univariate optimization, and the function that I'm talking about here, that we are finding the maximum or minimum values, it is an objective function. An objective function. Objective. We call it an objective function. So in univariate optimization, the function or the objective function depends on a single independent variable. E.g., you could talk of y is a function of x. X is the independent variable, so just one independent variable. So we are going to be optimizing such kind of functions where the dependent variable is just one. So having explained what we mean by optimization and univariate optimization, let us look at some two examples to be able to illustrate this concept of differentiation in optimization problems. So I'm going straight away to example 1. Example number 1. I want us to look at 2 or 3 examples. So we start with example number 1. So in this example number 1, we are told that a box with a square base and an open top is to have a volume of 62.5 centimeters cubed. We are asked to neglect the thickness of the material used to make the box and find the dimensions of the box that will minimize the amount of material used. So the best way to tackle this problem is to sketch the box in question. So this box is just like a cuboid where the base is a square. So we are going to sketch it, a box. We sketch just a rough sketch of that box. something like this. So remember, the top is open. Take note of that, an open top. This is the base, which is a square. So all these sides are equal because the base is square. All the sides are equal. Length and width equal. And you take note that the top is open. So it is not there. That top is open. It is not there. Remember, a cuboid has 6 faces, a closed cuboid. If you have the top to be open, then we have 5 faces. Now, we don't know the dimensions of this box, but all we know is that the base is a square, so we can say let x, or the dimensions of the base, be x. Let x denote dimensions of the base. And we are going to use h to denote the height of the box. Let h be the height of the box. So, how do you find the volume of a cuboid? Let V denote volume of the box. So you know that volume is equals to length times width times height. Length times width times height. But our length is x and width is also x. So that will be equal to x times h, which is the same as x squared h. That's our volume. Now, what are we told? That this box is to have a volume of 62.5 centimeters cubed. So we are saying that given that volume should be equal to 62.5 centimeters cubed, it means that x squared h should be equal to 62.5, which means further that you can make h the subject. It is equals to 62.5 over x squared. That one we now have. We are asked to neglect the thickness of the material used to make the box, and we are asked again to find the dimensions that will minimize the amount of material used. You see, when you talk of the amount of material used, then we have to take note of the surface area of that open box. You see, every face you have to buy, if it is a box, whether it is metallic, every face is made of metal, which you have to buy. So when you are buying, you need to minimize the cost. And so we need to minimize the amount of material that we buy. So let's find the surface area. So again, we are going to say let S denote the surface area of the box. So how do you find surface area? Remember, now we have how many faces? There are 5 because the top is open. So the surface area is given by S is equals to, the base is x times x, which is x squared. That's the base. Plus, look at the sides. Already we have taken care of the base, which is this. Let's take care of the side. This is side number 2. The base is number 1. This side number 2 and number 3. Number 2 and number 3 are the same. So those are rectangles. What is the area? of those rectangles. There are two of them, so 2 times x times h. The area of each of them is x times h plus. There are other two sides which are the same. Number 4 is this one, and number 5 is hidden. So there are two of them. Number 5 is hidden. So again, we are going to say it is 2 times, what about the dimensions? Again, it is x times h. So this will give you x squared plus 4hx. But I know h. So you need to replace h, replace h. Look at our h, it is 62.5 over x squared. So that our surface area can now be written as x squared plus 4 times h, which is 62.5 over x squared, and this is times x. When you simplify, you're going to get x squared plus, let us take 62.5, multiply that by 4. What are we supposed to get? That should give us 250. 250, and that is over x, because one of the x will cancel. You see here, this x here will cancel with one of the x, so that we have x in the denominator. So that is the equation for the surface area. So we can just say that therefore our surface area is equals to x squared plus 250 over x. So we want to minimize the surface area. The task is to minimize the surface area. So I told you, every time you talk of maximizing or minimizing any given function, you must know that the derivative must be equal to 0 at a maximum or a minimum point. So the task is, our task here is, to minimize s, minimize s. So you can say at the optimum of s, we know that derivative of s with respect to x must be equal to 0. So let's find those derivatives. So you can say now ds dx. Differentiate, that will be 2x minus 250 over x squared. That is the first derivative. What about the second derivative? You talk of d squared s dx squared. That's the same as 2 plus 500 over x cubed. That's what we get as the second derivative. So we know that ds over dx must be equal to 0. So we equate that to 0 and solve for x. So from here, we are going to get 2x minus 250 over x squared should be equal to 0. So from there, are we able to find x? Yes, let me rewrite this. This is the same as 2x is equals to 250 over x squared. Or you can write this as x cubed is 250 over 2. That is the same as 125. So you can now find x to be the cube root of 125. So you can say therefore x is the cube root of 125, which is the same as 5 5 centimeters. What about h? When x is 5 centimeters, you can find h. Therefore, so this implies that h, we said h is 62.5 over x squared, and our x is 5. You square that. So that is 62.5 over 25. You can press that in the calculator and see what you're going to get. 62.5 divided by 25, that will give you 2.5. So that is 2.5 centimeters. We don't know whether the values that we have found will be able to give us the minimum surface area. You are not sure yet until we test using the second derivative test that surely the values that you have found for x and h are the values that will give us the minimum surface area of that open box. So the next thing is to use second derivative test. Use second derivative test. I want to know what is the value of the second derivative at x is equals to 5 and h is equals to 2.5. So this is what you're going to do. D squared is dx squared at x is equals to 5. What are we going to get? That will be equal to 2 plus 500 over 5 cubed. We can press that. 2 plus 500 divided by 5 cubed is the same as 125. So the answer there is 6. 6. And 6 is greater than 0. So what does it mean? That therefore, this means that x is equals to 5 centimeter and h is equals to 2.5 centimeter. These values give the minimum surface area of the box. Of course, the open box. So we have now shown that if we use x to be 5 and h to be 2.5, then we are going to minimize on the amount of the material used to make the box. So that is the first question. Another question is this one. Let me write it. So you can write example number 2. Example 2. I want to do one more example to be able to illustrate that concept. So we look at example 2, and in this example 2, this is the question that we are asked to solve. So in this example number 2, we are given the question that a compound owner wants to enclose a rectangular field adjacent to a river. The owner wants the field to contain 125,000 square meters. No fencing is required along the river. And then we are asked to find the dimensions that will use the least amount of fencing. So again, let's sketch. It's better to work with a sketch. Let us sketch this kind of a field. You see, this field is rectangular. It's a rectangular field. And this is how the sketch looks like. We have this kind of a field that you're sketching. And let's say the river this side. This side we have the river. This is the river. With some water that is flowing. So that, let's say that's the river. So we don't fence the other side. So we are going to say let the length of this rectangle be L and the width be W. What else are we told? That the area must be equal to 125,000 meters square. So we need the dimensions. What is the value of length and the value of width that will use the least amount of fencing? So how do we find the area of a rectangle? We know that area of a rectangle is given by length times width. And that area is supposed to be 125,000. So we say from the given information, we are told that length times width is supposed to be 125,000. From here, it means that I can make length as subject of the formula. That is 125,000 over the width. Now, if we are to minimize the amount of the fencing, you see fencing, we talk of the perimeter. What is the length? The whole of that fencing. What will be the length of the wire that you are using to fence that kind of a garden? That means we'll be talking of perimeter of the wire that we have used. So let P denote perimeter. The perimeter that you have fenced. So we know perimeter is given by, perimeter is equals to, from here we have length plus 2W. That's the perimeter of the wire that we are going to use in fencing. But I need to replace L. Replace L. Look at our L. It is 125,000 over W. So therefore, we are going to get our perimeter to be 125,000 over W plus 2W. So our task is, to minimize the perimeter. Minimize the perimeter. And what you know is that at optimal perimeter, optimal means maximum or minimum, we know that dP with respect to W should give us 0. You see now P is a function of W. Now it is not X. It is now W. So from here, let's get the derivative. So you can say now dP dW. When you differentiate, you're going to get negative 125,000 over W squared plus 2. What about the second derivative? D squared P dw squared. This is the same as 125,000 times 2. That will give us 250,000 over w cubed plus 0. Derivative of 2 is 0. So now when we equate dp dw to 0 and then solve for w, what are we going to get? So from here, this one will now give us negative 125,000 over w squared plus 2 should be equal to 0. Or you can write this as 2 is equals to 125,000 over w squared, which means w squared is equals to 125,000, and that one you divide by 2. 125,000 divided by 2, let's see. 125,000 divided by 2, that should give you 62,500. 62,500. W squared is 62,500. So from here, we can't be able to find W. So you can just say, therefore, W is the square root of 62,500, and that is 250. What about L? Width is 250. What about the length? So we know the relation between length and width. So when width is 250, it can be easy for us to find the length. So this implies that our length is equals to 125,000 over W, which is 250. And so this is equals to, remember this is in meters. What about 125,000 over 250? You can press that in your calculator. That will give you 500. So this is 500 meters. But you see, we are not sure whether these values of length and width will give us the minimum perimeter. We have to use the second derivative test. So what we do is use second derivative test. I'll write this side. Use second derivative test. Let's see the value of d squared p dx squared at w is equals to 250 meters. So d squared p dx squared, not x, that was w. So let me change. Here we are talking of w, not x. D squared p dw squared at w is equals to 250. What will this give us? When you substitute w is 250, we are going to get 250,000 over 250 squared. What is that? No, is this squared or cubed? No, it was over w cubed. So this is cubed. And what will this give us? 250,000. You can press that in your calculator and see what you're going to get. 250,000. Then divide by 250, and this is supposed to be cubed. That is 0.016. 0.016. And this is positive. This is greater than 0. So what does it mean? That when you get a positive value, then it means that those dimensions that we have found will give us the minimum perimeter. So this implies that the dimensions which we found as W is equals to 50 meters and length is equals to 500 meters. These dimensions give the minimum perimeter. So for you to minimize on the amount of the material or simply the wire that you're using to fence the compound, then you have to use the length as 500 meters and the width as 250 meters. And when you multiply, you get the area to be 125,000 meters squared. You could also get the total perimeter, L plus 2W, so that you get the answer. Perimeter will be equal to 1,000 meters that you need to fence. One last example on the optimization problems is example number 3. You see, once I do example 1, 2, all the way up to 3, then it means if you find any question in this area, you should be able to tackle it. So we write example number 3. And in this example, this is the question that we are asked. So in this example number 3, we are given this question that coughing causes the trachea or windpipe to contract, which in turn affects the speed of the air through the trachea. The speed of the air during coughing can be modeled by the equation V is equals to K times R minus R in bracket times R squared for 0 less or equal to the small r less or equal to the capital R, where K is a positive constant. The capital R is the normal radius of the trachea before coughing, and the small r is the radius during coughing. What radius r will produce the maximum air speed? Look at the question. We are asked to find the value of the r, the small r, that produces the maximum speed. So we need to maximize the speed. At what value of r will the speed of the air through the trachea be maximum? So I told you at optimal values, the derivative of that function must be equal to 0. So we write solution, we write at optimal value of the speed, what we know is that derivative of v with respect to r must be equal to 0. Remember, take note that the r capital is a constant. The normal radius of the windpipe before coughing, it is a constant value. The K is also a constant. So from here, V, the speed, is a function of the radius of coughing, the coughing radius, or the radius of the trachea just after coughing or during coughing. It's a function of, and that's why we are finding dV dr is equals to 0. So let's find those derivatives. You can say now dV dr is equals to what? Let's differentiate this equation, the one we have been given, this one. Of course, I can see there's a product of two functions of r, this and this. So one of them is u. We are going to use product rule to differentiate that function. Or you could open the bracket and then differentiate using power rule. The best way is to use power rule. Take note that from there, v can be written as, if I open the bracket, I'll be having k into r times r squared minus r cubed. So use power rule to differentiate that with respect to r. So we are going to get k outside, then 2r times r minus 3r squared. What about the second derivative? D squared v. That should be v. Let me write in a proper manner. D squared v with respect to r twice. That should give us k into 2r minus 6r. K into 2r minus 6 small r. Look at the first derivative. So when we equate it to 0, what are we going to get? So this one equate to 0. Therefore, that equation will now look like this. K times 2r times the small r minus 3r squared should be equal to 0. This can be written as, because I can see the small r is common. So if I factor that out, I will have k times the small r in bracket 2r capital minus 3r is equals to 0. And you see k is positive and it's a constant. You can divide both sides by k to get this. Now when you divide both sides by k, you're going to get r into 2r minus 3r. That should be able to give us 0. So that equation, we are multiplying two factors and the result is 0. It simply means that therefore either the small r is 0 or 2r minus 3r is equals to 0. From here, you're going to get the small r as a function of the capital R, that is 2r over 3. So look at the values we have found. R is equals to 0. Another value is that r is equals to 2 over 3 times the capital R. Now, we don't know which of those values will give us the maximum air velocity. So, to know whether which one is maximum or which one is minimum, we are going to use the second derivative test. So you write here, use second derivative test to know which one will give us the maximum air velocity and which one will yield the minimum air velocity. So let's start with at r is equals to 0. Let me use another color. You can say at r is equals to 0, what will we get as our second derivative? D squared v with respect to r twice. What will be that value? It will be k into 2r minus 6 times 0, which is simply equal to 2k times r. K is positive, r is also positive. Radius can never be negative. This value is greater than 0 because k is positive and that r capital is also positive, not 0. So what does it mean? That therefore, this means that r is equals to 0 produces the minimum minimum air velocity or air speed. We talk of speed. Minimum air speed. We wanted the one that produces maximum. Let's see whether the other one will give us maximum air speed. So again, do the same thing. You can write at R is equals to 2R over 3. What will be our second derivative? D squared V with respect to R twice is equals to, I'm replacing the small r, so that is K into 2R minus 6 times 2R over 3, which is simply equal to K into 2R minus 4R. And this is equals to negative 2KR. K is positive, R is positive. This is a value less than 0. So therefore, what does it mean? That therefore, R is equals to 2R over 3 produces the maximum air speed. So that's the answer, that the value that will give us the maximum airspeed is when the small r is equals to 2r capital divided by 3. So when you find any other question involving univariate optimization, you should be able to tackle it. It is easy as long as you can be able to find the first derivative and the second derivative. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Professor Francis Okech, and you will find me right there. Also, comment, like, and share this video. When we meet next time, we look at other problems in applications of differential calculus in real life situations. Bye-bye.